Now let a and b be integer. I have drawn some of the integer multiples of b along the number line. And a is also somewhere along the number line. So maybe a is, say, here. Maybe this is a. Well, then a has two closest integer multiples of b. In this case 3b and 4b. So that I can take the integer multiple of b that is closest but less than a. In this case 3b. So a is 3b plus something. And what we miss is this distance. So let's call this distance r. And then a is 3b plus r. And r has another property. R is between 0 is less than or equal to r, and strictly less than b. So the distance between two consecutive multiples of b is always b, so this r has to be less than b, because b is the distance between 3b and 4b. In general, if I don't know where a is, then I can, no matter where a is situated, I can know that a is either one of the multiples of b, so I can write a as b times q, where q is an integer. That is in the case where a is one of these points. If a is not one of these points, then a is strictly between two of them, two consecutive points. So if I go to, let bq be the multiple of b, which is the greatest one less than a, that means it is the one just to the left of a along the number line. Well, then a is that number plus a number less than b, because if this number was more than b, then a would be between another pair of consecutive integers. So if this one is the closest multiple of b to the left of a, then r is strictly between, well, it's greater than or equal to 0 and less than b. So 0 is less than or equal to r, and r is less than b. So for any integers a and b, I can always write a as b times some quotient plus a remainder less than b. And that is the content, half of the content of the Quotient-Remainder Theorem. The rest of the content is that this can be done in only one way.